Welcome. Okay. Hello, everyone. Welcome to today's research salon. And in today, I'm going to present a paper titled "Over-the-Air Computation Systems: the Optimization, Analysis, and Scaling Laws." So, during my presentation, I will not only introduce this paper, but talk a little bit more about the wireless federated learning as well. So let's get started. Um, okay. Here is the outline today. First, I will give you the motivation of this paper and then talk about the outcome and federated learning. Then I will show some computational optimal outcome in this paper. And finally, the scaling performance and draw a conclusion. So to begin with, let's talk about the motivation of the over-the-air computation. It is basically from the concerns on the limited radio resources. For some applications, such as over-the-air consensus and wireless distributed machine learning, it involves a massive number of participants. So if let each participant to occupy orthogonal radio resources, it will suddenly become insufficient and it will result in a transmission delay. For example, the machine learning models always own thousands of parameters for each client. If we transmit them in orthogonal multiplexing, the resource cost is huge. And for TDMA, the transmission time for one communication round for all these users may not be tolerated. And for the first scenario, the over-the-air consensus, we notice that although there is many data here, we're not interested in the individual data. Instead, we're interested in the summary of data, especially in the large or dense sensor networks. And these functions are very simple. For example, we can calculate average, sum, or mean, or max function, and so on. We can calculate this function in over the air, and it includes both the linear and nonlinear functions. These functions can be computed during transmission, so it can be called the over-the-air computation, and this is first given in the following paper. And now we have two options in this scenario. The one is we can still transmit all the data to the cluster head and do the computation. The other one is we can jointly transmit using the same time frequency block. And for this one, we need a new protocol, and it can be spectral efficient. As another interesting topic, the over-the-air computation can be also used in the wireless federated learning. And here is the framework for the traditional one. In the first step, all the clients will send its encrypted gradients to the server. And at the server side, it will do a secure aggregation and send back the model updates to each client. And at the client side, they will update their models locally. When the edge devices participate in the learning process and share the wireless medium to transmit the updates to the edge server, the radio resources can be limited, and it will cause a severe congestion of the air interface, resulting in a communication bottleneck for the federated learning. And here is the framework if we are using the over-the-air federated learning. So in this framework, if the over-the-air computation is being used, the first step is the same, that the server will broadcast the model to each client. After each client do the local computing, they will update their models to the server, but using over-the-air aggregation. So it uses the linear channel superposition property, and it can the weighted sum, that is the fidelity average, can be computed during the transmission. So as a result, it will dramatically reduce the resources for the fidelity learning. So that is over-the-air fidelity learning. And let's move on to the LComp and the fidelity learning. So the LComp fidelity learning, I forgot to say, the LComp is just the over-the-air computation. So the LComp fidelity learning has been studied in many literatures, and here I choose this one from Dr. Kaibing Huang's group called the one-bit over-the-air aggregation. And in this work, the OFDM modulation is adopted for the wideband transmission, and the total bandwidth B will be divided into n orthogonal subchannels. Each subcarrier is orthogonal to each other, and it can transmit multiple symbols parallelly. For each subcarrier, the fixed digital constellation is implied by all the devices, and they map each gradient element to one digital symbol. For the corresponding input vector is the local gradient. We assume for the case user will have in total Q gradients to be transmitted. In each element in this vector, it represents the gradient in it represents the symbols loaded on orthogonal subcarriers. So we know that we have Q in total, and we can transmit M subcarriers in one OFDM symbols. So as a result, we will need NS equals to Q divided by N OFDM symbols. So
quick question, Chenpei. So the J tilde K1, K2, in general, J tilde Ki is, in terms of value, it's either 1 or 0,
right? In this paper, yes, because they're using a one-bit transmission. Yeah, I will talk about the BPSK later. So here is just the channel input vector, which means the source. And the over-the-air process in the channel is afterwards, as located on the subcarrier level. So on each subcarrier, from the all K users, the received signal equals to the sum from all the individuals. And you can see in this equation, the HK is a channel coefficient, and the PK here is a scalar, follows the power control policy, and the Z here is the channel noise. So the target of this over-the-air computation is to make it closer to our desired weighted sum, that is the fidelity average. So how can we do that?
Oh, another quick question. For NS here, NS should be an integer, right? It's not going to be a real number, right? So
this NS,
yes.
Yeah, it should be an integer. So there must be a ceiling here.
Yeah, it must be a ceiling over there. Yeah. Okay.
Yeah. And here is these three terms. And so the first step is to design the transmitter. And I want to say, just like Dr. Pai mentioned, in this paper, they're using BPSK, and it is a one-bit quantization, but for the LComp, they always use analog or AM modulation. That means the GK here is a real number, but in this paper, it's either 1 or 0 after the BPSK modulation, so it will be either 1 or -1. It is used for, it is because it needs better integrate with the sign SGD. So they found that BPSK modulation is exactly the one that keep the sign information. At the same time, it also follows the channel superposition property, just like the AM and analog modulation. Here is the channel inversion process. This process is to eliminate the various impacts or the different channel realizations from the fading channel. So here they adopt the power control policy to compensate the channel hostiles and provide a uniform amplitude if for the unit value. So in this way, we can ensure that the computation results will be correct. And I'll talk about it later in the following section. So at the receiver side, they use a majority voting to aggregate the transmitted gradients. And the over-the-air aggregation is shown in this equation. This is the received signal at the receiving antenna. So it is still a vector with m elements that is the same with the OFDM subcarrier numbers. And the GK here is the truncated gradient that only keeps the sign of the sign of each gradient. And after that, this is the receiving vector, and the decoder is based on the majority voting. So the V here is to keep the sign of this vector and use this V for the aggregation. Instead of digging it into the designs for this 1-bit outcome federated learning, I want to go back to the paper I presented today to look at the outcome only. How close we can approach the desired value using the over-the-air computation and how it can be scaled to a larger sensor network. So here are the related works. The first category focus on the different over-the-air computation functions. So as I mentioned, they want to compute the sum or other linear and non-linear functions in an ideal channel. And for second category falls into the performance analysis on the practical wireless multiple access channel. So they compute the function in the form of sum or weighted sum, but the channel is not ideal. So it will have the fading and the channel noise. This paper belongs here. So it's analyzed the performance on the practical wireless channel. And let's look at the system model again and be familiar with denotations in this paper. The K sensors measurements, that is the source, is denoted as K1, K2 to the X1, X2, and XK. So for each user, it will first at the receiver side multiplied by a transmitter scaling factor, BI. This BI follows the power control, and the HI here is the estimated channel coefficient. I want to stress that the H1 here is a real number because it should be a complex number, but in this case, the phase should be compensated. So the only thing that is that's of our interest is the absolute value of the channel coefficient. So here is the channel, and after the pre-processed signal multiplied with the channel coefficient, will superpose each other and added by a channel noise. So at the receiver side, it will first apply a receiving scaling factor that will link the converts the voltage of the current directly from the antenna to the value it represents in the digital domain. So here is the receiving scaling factor here. It works in the digital domain. And at last, we will have our output R here. So on the right-hand side, here I list some functions. I list some functions here. The function here is the R equals to A multiplied by the superimposed signal plus the channel noise. That is our desired function, and we want it to be as close as the desired validated average. And the distortion is evaluated by the mean square error, the MSE. And for the power consumption in this system, it is the actually the transmitting scaling factor square and sum them up. That is the total power consumption in the opposite outcome system. The optimization problem is to minimize the mean square error under the power constraint. And here are three keys instead in front of the solving this problem. The first key is the transmitting scaling factor devotes the power to improve the SNR, the signal to noise ratio. So if we have a larger transmitting scaling factor, it means we are using more power, while the receiving scaling factor do not sacrifice in power. It is only a multiplication in the digital domain, and it will amplify the channel noise in this process. And the second one is we assume the channel coefficient are known by both the transmitter and the receiver. So here we also assume there is a perfect channel estimation and synchronizations here, and there is a powerful feedback in this system. And the third part is the preprocessed signal are assumed to have zero mean unit variance and they are independent with each other. So it is the assumption on the source. And let's solve this problem. First, the problem formulation is shown here. We want to minimize the mean square error. And A here is the receiving scaling factor, and BK is the individual transmitting scaling factor. And we want the transmit power well smaller than the power constraint. And the mean square error is shown in this equation. Notice that if we fix the A or fix BK here, the MSE or the objective function is actually convex. So it implies us to use the alternating direction method. So the first step to solve this problem is to sort the channel coefficient ascendingly and fix the A. It's shown in this equation, and then the whole region that's the optimal A may falls in is divided into K subregions. Under these conditions, we can solve this optimization problem by fixing A, and we know that the optimal BK will be shown here since it's convex optimization. And the interpretation is we divide the overall user into two classes. For the first class of the user, they have a small index of the channel. So it means they have poor channel conditions. And for the second class of user, since the index is big, they can consider as they have a good channel condition. And for the first class of user, they are required to transmit at full power. And for the second class of user, since they have a moderate or they have relative good channel conditions, all they need to do is to inverse the channel's impact. And we can substitute the optimal BK back into the MSE, and we found only the second class of only the first class of user will contribute to the first term of error. This term is the misalignment error. It is caused by the different by the channel fading for the different transmitting power, and the second term is basically from the channel noise and amplified by the receiving scaling factor. So the next step is based on this optimal BK here, how can we solve the optimal A in this equation? And for the step 2, we also know that solving this optimal A is equivalent to find a critical number I, because this because we insert the K into this equation, finding an optimal A is another complex optimization. So the only difficulty is to how we divide the users into the two classes I just mentioned. Um, so since it is a quadratic function, if we have this critical number, that means we know that A falls in some subregion Si, and this is a quadratic function, and the final result can only be optimal here without this constraint or on the boundary of this constraint. And for brevity, the optimal result for this optimization problems is given directly shown here. The GI here is the optimal value without this constraint that A belongs to Si, and finding the optimal critical number is to find an index that makes the GI goes to the maximum. So finally, the optimal MSE and power consumptions are listed as follows. The MSE will equals to this will showing here, and the power consumption you can also check. It has two parts. The first part is the full power transfer user, and the second part is the channel inversion user. So it also consists of two classes. And at last,
before you go, could you go back to, so here, could you previous page, please?
okay.
So here's the optimization objective is, the MSE minimization, right? But
Yeah.
we all know that, MSE is kind of second order, this kind of variable, variance, right? So that's the reason why for your solution BK, we can classify all the users into two categories. So my question is that possible? We can have even higher order objective. Say, for example, we just try to minimize certain kind of a distribution of error or whatever, right? Just higher order. Instead of 2 order, we can go to 3 orders, 4 orders, or even more. In that way, we can, classify all the users into more fine-grained groups, say 2, 3 groups, 4 groups, or even more groups. You got my question, right?
I know your questions. You mean we're not using the second order order statistics.
Yeah.
So we are minimizing some other functions.
Yeah, for example, just like some say var or cvar, or any kind of a risk averse, optimization objective, right? So something like that. So is that possible?
I doubt it's I don't know. I think the solution may be different, because this solution is actually because of the convexity, if we fix the A, so it will give us a quadratic function and it's convex, and then we can solve it in this shape. But if it's higher order, I doubt it will have the same grouping or some other styles that the user will foresee.
That's true, but what I mean is, in this way, I know if you formulate in this way, I mean, MSE probably have some physical meaning. Probably MSE is good enough, but probably it's not good enough, right? So, I mean, even we formulate that into a higher order optimization problem, it depends. You can formulate it into, say, stochastic optimization. We can still find possible solutions.
If it can be solved, yes, I agree. But the result may be a lot different, I guess. Yeah. Yeah, because if we only consider the mean square error, it has physical meaning. Yeah, that means the noise variance, the noise power. So we can easily find that the MSE here, the two terms all have its physical meaning. The first one is the fading causes the fading caused misalignment, and the second term is channel noise caused uncertainty. So it has, if we consider this as a noise signal, it has two components. But if for the higher order statistics, I have to say I don't know. But if we can formulate that problem,
Yeah.
maybe we can.
Yeah, I got your point. Yes, it has a physical meaning. It's discretized. Also, probably that can map to your receiver design or transmitter design as well. If you formulate that into higher order problem, potentially we need to convert that into the continuous one. Then we try to discretize that for the solution. Then that's going to complicate the, okay, that's going to complicate the transducer designs as well, right? So
yeah, for all the outcome paper I read, I think they evaluate based on, they all evaluated based on the MSE, and sometimes they they transform the MSE into some rate-like functions. For example, they just regard this as a noise signal, and they can derive the signal to noise ratio. Finally, they can insert that into the Shannon capacity equations. So you will, they say that is the rate for the outcome system, and they just use this rate to do the scheduling, the resource allocation, something like that. But I think behind this, it's always the mean square error.
Yeah. I understand. It serves the purpose. Also, it's suited for this one. But I'm just talking about it from a theoretical point of view. You know, second order sometimes not good enough. Probably higher order can give you better control of BK and
yeah, I agree with that. But
yeah.
from now, I'm not familiar with the higher order. Maybe after that we can dig into.
No, I don't, not necessary. And I think that's only have theoretical value because, like I said, if you use the second order, it also simplifies the transducer design, right? So if you want to find a high order, I'm not sure that it increases too much complexity for the transducer design.
Yeah.
Yeah. Okay. Yeah. Please go ahead.
I have a question. So yeah, for this formulation, I wonder. So what's the difference for such formulation? You know, for the computation over the air with federated learning, compare to some general task using the computation over the air.
Yes. Actually, it is a comparison called over the sum of MSE and the MSE of sum. So for the general one, if you check this paper, it actually have a section there. But yeah, they use the norma, and the norma is just another multiple access. So basically, if we compare it to norma, it's just a multi-user detection. So
sorry, what is norma?
The non-orthogonal multiple access. So it is it is also like in the same shape that all the users transmit their signals simultaneously, but the receiver can decode the first user, because the first user have the biggest SNR, and after the decoding, it will subtract the decoded message from the first user and then decode the second biggest SNR user, so on and so forth.
So why the first user has the most, like the highest SNR?
Because it has the biggest power, using the biggest power, and all they have the best channel conditions. But it depends on it is
The first user, you mean the first user, the first data transmitted over the air. That's what you mean, the first user.
No, I mean,
how do you define what is the first user?
The first user is defined as the user with the biggest SNR. Yeah, my mistake.
Okay. So which means the user has the highest transmission power and has the most the high quality signals, right?
Yeah. So
okay.
that is the normal, and they use the successive interference cancellation. It's just like what I said, to decode them one by one. So for that, it's the sum. The evaluation is the sum of MSE. But for the over-the-air computation, it is at the receiving antenna. The direct signal we can pick it up is the aggregated signal. It's already the sum, so we can only evaluate the MSE of the sum.
I know what is using the computation over the air. So my question is, we can use the over the air computation to do something, to some general computation, right? Not federated learning, right?
Yeah.
For example, if I wanted to do something like MapReduce, okay, I try to map some data to some tuples, and then I wanted to aggregate over the air, right? So basically, computation over the air is you want to do some aggregation over the air, right? Or computation over the air. But here you combine over the air computation with federated learning. So my question is, what is the key difference? Okay, the key challenge when you apply federated learning with computation over the air, compared to general computation tasks using computation over the air. For example, MapReduce over the air.
I think it's you understand it inversely. So I mean, I want to say the outcome or the over-the-air computation is for federated learning, not the federated learning for the outcome. So we want to use this tool to save the bandwidth, and for the federated learning, and a communication round will need to update thousands or millions of parameters. So if we let all the users transmit them all to the server, it will consume a large bandwidth. But if
I know the advantage of computation over the air, but I can use the computation over the air to solve a general problem, right?
Yes.
But here you use it for federated learning. I know, because the advantage of computation over the air is we can do the aggregation, federated aggregation over the air, right?
Yeah.
But as we all know, the computation over the air is not created particularly for federated learning. It's not invented for federated learning, right?
Yes.
Then when you use the computation over the air for federated learning, there should be some key challenge, right? Otherwise, this paper is like we use a general method and we have some general challenges to solve federated learning. And this federated learning task could be any other distributed computing tasks, right? Then you can optimize it not only for federated learning. Say the paper could be using the optimizing computation over the air for distributed computing. right?
Yeah, actually, this paper is for the sensor network. So,
So it's
only,
not only for federated learning, right?
yeah, it's not only.
I see. I see. So that's my question. Say, because when you present all this, it's like, you know, all the formulation here is designed for federated learning, but I did not see any, you know, unique challenge or unique objectives only for federated learning.
I think it's only for wireless communication.
I see. So it's not only for federated learning, right?
Absolutely, it's not only for federated learning. You can apply it to
Then,
other tasks as well. So,
okay. So if you wanted to, you know, use the computation over the air for federated learning, do you think like any key challenges here if you wanted to apply this to for federated learning?
I think the key challenge here,
Yeah.
if you are talking about the, actually, I don't think there. We can only say that the computation results accuracy will affect the federated learning convergence.
Yeah, I think that's a problem. That's a key point, Chenpei. Probably the arrow, for example, the MSE for this round aggregation, that's going to have cascading impacts over the iterations, right? Or say it's going to propagate through the multi-round after this, and even have some significant impacts on the final convergence or transmission, training loss or whatever, or learning accuracy you got. Also, this is the only one round MSE. If you consider, you know, multiple round during each round, we need to do this. I think it's not a small problem, right, to consider. So what's this kind of errors impacts on the learning performance? Yeah.
Yeah.
Yeah. So the question is like, you know, so why we want to, you know, use the over the air computation for federated learning, and what is the unique challenge if you want to, you know, use it for federated learning, right? For this formulation, you probably need to rethink the formulation for federated learning to make it more like you know, aligned to the objective of federated learning, involving, you know, more metrics of like model accuracy, the gradients, you know, the model updates every round, and the final model accuracy we can achieve for federated learning, right?
Yeah, I totally agree with you. So
yeah,
that is
so
also that's confused me for quite a long time now. But now,
yeah, I think Dr. Huang make a very good point. You know, we all know that general benefit of using over-the-air computation in fed learning is that we can improve the spectrum efficiency, we can do communication efficiency, efficient fed learning. That's pretty obvious, right? But honestly, I think the challenge here, if you don't consider this kind of a physical layer error, you just consider the general, you know, error-free over there computation, probably we don't find much challenge. But if you consider the arrow related over there computation, you know, probably another good formulation should be considered. Should be another good problem should be formulated to think.
yeah,
Check the errors impacts on the fed learning performance. Right?
yes, that's true. So for this paper, they just want to get accurate enough results. So if we involve in more,
I want to say is, if you want to compare, if we want to do a fair comparison, you should also consider certain kind of imperfect wireless transmission, without using over there computation, right? So say each client, they submitted their gradients to the server, but that transmission also affected by the channel conditions. It's not error-free. So compare with over the air, you introduce certain kind of other errors. You compare these two schemes, right? And compare the final learning performance, stuff like that.
Yes, that's true. Because, but for the higher layer communication, that's already error-free, right? If there are some redundancy check, and if the signal strength is too low, they may ask for a retransmission. But I think for those kind of communication,
no, you cannot put everything together, then the things will mess up, right? So you need to simplify, separate the case by case. So if you consider this physical layer things, your benchmark will consider physical layer only. You cannot say, okay, upper layer I have error-free, I have a checking, I can ask for retransmission. You cannot consider all of this.
Yeah, so what I mean is, so the LCOM is physical layer stuff. And for some existing, if you consider the communication in the federated learning, they are higher layer stuff, right? They do not consider so much.
You need to exclude the higher layer, only physical layer. You need to exclude higher layer. Like I said, for the research, for the comparison, you cannot consider everything, right? For example, today's communication, we involve very limited error, right? We cannot say it's perfect, but it's a very limited error. But when you do research, you cannot consider, you say this is a physical layer approach, but you want to compare something with physical layer, MAC layer, networking layers, the whole package, whole stack. It's mission impossible. You can be better than them, right? So yeah, if we talk about the physical layer, leave everything to the physical layer.
Yeah, so that's my, I understand. Okay.
Yeah. Please move on, please.
Okay, sorry, I cannot answer Dr. Fang's questions right now. So just move on and leave it in the discussion. Where am I? Oh, okay, here. Here is the scaling performance. But before that, there are two benchmark policies. The first one is the channel inversion policy. That is basically lets all the users to invert their channel, and it's equivalent to set the critical number equals to 1. And the second one is the energy greedy policy. And this policy is let all the users to forced to the full power transfer. So it's equivalent to set the critical number equals to k. And they also propose a suboptimal policy, and they define the policy is computational effective if and only if the averaging mean square error equals to 0 as the k approaching infinity. And for the policy is energy efficient, that is for the policy's averaging power vanishes as the k goes to the infinity. First,
sorry, I got a question here. What do you mean communication effective? This kind of communication, computation effective. I mean, this computation is kind of automatic aggregate or compute over there, right? So it's not like certain kind of machine need to aggregate that, right?
I think this is talking about some scaling capability. When you get more and more sensors, you get a larger sensor network, the MSE will equals to 0. So that they means computational effective. Just like that in in the massive MIME or something for that.
No, no, no. What my question is, this is computation effective for whom?
For who? The over there computation, the result, the expectation, the averaging MSE, I mean. So no matter how many users are there in the over there computation, it has an MSE, right? So if that's it's not
No. Let me clarify my question. Okay. So if we consider physical environment, physical scenario, right? So several transmitter is going to transmit to things to the server or aggregator, whatever, right? So even sensor network, file learning, it doesn't matter, right?
Okay.
So this computation effective is for any of the transmitter or for the receiver, or is for who do the optimization? So that's my question. Is computation effective for whom?
It's actually for, I think it's
for the optimizer.
Yeah, it must be an overall result. So it cannot for some individual user. It is for the aggregated result. So it's as the aggregate.
So it's going to be for the executor of the optimization, right?
It's not that relevant to the optimization. So they already have that optimization policy and some benchmark policy, and they just want to show that different policy results in an MSE, and this MSE has can that policy be scaled into larger sensor network? So it's just computes the MSE divided by K, regardless whether or what kind of optimization they are using. They just want to compare that, which one is better. I don't know if I answered your question, but.
So it is for the whole system.
Yeah, it's for the whole system.
Yeah, when you increase the number of sensors or the K, your system computation in terms of the over the air computation, the MSE reduces faster than the linear increase in the number of nodes.
Yeah, in other words, is computation effective for the formulated problem or for the algorithm, right? Or for the guy who is going to execute the algorithm?
Yeah, that's true.
Yes, that's exactly my question, right? So
the policy itself.
Yeah, computation effective for who, right? So it's not for the transmitter, it's not for the receiver, but just in case if the receiver will be the guy who is going to do the optimization, it's going to be computation effective for whom? For the receiver, right? But the energy, yeah.
So yeah, that's for the overall system, and actually it's the base station to conduct that optimization. So
but the energy efficient for whom? Is also for the
efficient for the transmitter, the overall, because the receiver is just receiving the signal, but we only consider the transmitting power. So it's all the averaging transmitting power divided by K.
Well, yeah.
Yeah, the authors, I believe they just mean the whole system. So
that's true. That's true. But again, Chenpei, we are kind of engineer, right? So when they propose something, say, okay, it's computation effective, it's energy efficient, we need to know it's for which kind of components, right? Even the answer is for the algorithm, I can understand, right? So, but you need to clarify it's not computation effective for the ending users. Otherwise, if we put that into the machine learning, better learning, for example, that's going to confuse the reviewers as well.
Yeah, so I think this two definition is to show that, okay, which policy can be scaled to if the nodes increase, and they give us two matrix here. Matrix. Yeah. So, and this policy is proposed, and for this policy, it use a function to use a deterministic function to approximate the critical number. I mean, if you remember, the critical number is the result of that optimization problem, and it depends on the channel realization. But in this policy, they want to, when the k is large, they want to use the deterministic function to approximate that, and the corresponding receiving scaling factor and transmitting factor. And this policy does not depend on the channel realizations. So here are some simulation parameters, and I list the three results here, and it do has other simulations in their paper, but I just omit the multi-antenna ones and try to give the scaling results. So they transmit in their simulation, they set their transmission power at 10 and receiving noise power equals to 1. And they also assume that the channel follows the Rayleigh fading with the unit variance. And for the first figure, it shows that the first eye policy can be close to the real optimal one if we carefully choose that deterministic functions. And we can find here is the critical number. The critical number here is actually very small comparing to the number of sensors. And it is still a random number if you compute the optimal one, because there is a confidence region here. And the square root approximation just shows like upper bound of the computational optimal policy. And k to the 1/3 is another approximation that close to the computational optimal policy. From the second figure, we can find the benchmark 2, that is, that all the users transmit at full power is not computational effective since it doesn't vanish as k increase. And inaccurate approximation like this policy equals to k divided by 2 it is also not so good because it's cannot be regarded as computation effective as well. While the good approximation like the square root k shares a very similar trend with the optimal one, and it's also vanishes and be regarded as computational effective with the true computational optimal one. For the third figure, it considers the average power, and for the benchmark policy 1 shown in the yellow figure, if you remember, this policy is to let all the users to transmit to inverse the channel. So it highly depends on the worst channel condition from all that users, but it do give us the smallest power consumption, while the blue curve is the computation optimal, and we compare it with the red curve that is a very close approximation of the computational optimal. It shows that the first eye policy is showing a trade-off between the computation effectiveness with the power efficiency, because it shows a better power, a smaller power consumption as the k increase comparing to the computational optimal. And these two can be regarded as the energy efficient as well, because it do vanishes as the k increase for the inaccurate approximation and the benchmark policy 2. They are not energy efficient, and for the benchmark policy 2, if you remember that this policy is let all the users transmit at full power. So as the K increase, the transmission power will not change at all. So here are the three comparisons between these 5 policies, and here is the conclusion. Looking at this table, we can say as a summary, the computational optimum policy is both computationally effective and energy efficient, while these 2 benchmarks are not. And for a very close approximation on the computational optimal policy, it do have these 2 great properties as well. But if the approximation is not close to the computational optimal, it will not have these 2 properties. So the conclusion is drawn like for the derived computational optimal policy, it has a vanishing averaging MSE and the vanishing average power consumption with increasing number of sensors. And the first I policy that is in regards to the square root reviews the trade-off between the computational effectiveness and the energy efficiency. This one is important in the practical outcome system design because you do not need you do not need to compute the optimal value. The only thing you need to do is to use the channel feedback and sort that all the channel coefficients and put it into a deterministic function and compute the approximate critical number. So I do recommend all of you to check this paper because they do have other content in the paper because it's a journal paper, so it's so long for me to present them all. For the normal comparison with over-the-air computation, it also shows the sum of MSE and the MSE of sum in that paper, but I do not include that in this presentation. So you can ask me in the discussion. So that's all for my presentation, and any questions are welcome.
Thank you for Chenpei for the presentation. I'm going to stop recording first, then you guys can ask questions, okay?